תיאבון. בוקר טוב. אתה מבין את זה, כן? שי. אנחנו שמחים לארח היום את שאול אלמגור מהאוניברסיטה של אוקספורד. שאול אלמגור סיים את התוארים שלו באוניברסיטה העברית, בהצטיינות ליטרטורה ראשון, תואר שני בהצטיינות, אחרי זה דוקטורט אצל אורנה קופרמן. עובד במעבדה של ג'ואל מקנין באוקספורד בנושאים של תיאוריה של מודל צ'קינג, וריפיקציה. הוא יסביר לנו יותר.
אני מתנצל מראש שההרצאה תהיה באנגלית, כי זה פשוט לא עובר טוב בעברית. ניסיונות כושלים הראו. אז אוקיי. נשים גם הזמן שלי. Okay, I will talk about certifiable algorithms in automated verification. And before I get to what certifiable algorithms are, I'll start with a bit of background on automated verification. In verification, the basic paradigm is called model checking, and it is the following. We're given a system, either as a piece of code or as a finite state machine or in other formalisms, and we're given some specification, which is either a logical formula or some specification formalism that gives a property or a list of properties that we want the system to satisfy. And the basic paradigm says that we take these two, we pass them through a model checker, which runs some kind of checks, and it gives out an answer. Either yes, the system does satisfy the specification, or no, the system doesn't satisfy the specification. And if the answer is no, we also get a counterexample, which is some behavior of the system that violates the specification. So essentially, we're telling the designer, this is what you need to fix. Fix at least that either in your system or your specification, but this is wrong. So let's see a very short example of this. Here we have a finite state machine. On state 2, we generate requests. On state 5, we get grants. And the property we want to reason about is it true that in every behavior of the system, every request is eventually followed by a grant? And the behaviors we look at are infinite time behaviors in this context. So we have an infinite computation of the system, and we ask, is this true? And we can formulate this in linear temporal logic, for example, and other formalisms. It's not very important for this talk, but this is a linear temporal logic formula. So we take the specification, we take the system, we run them through a model checker, and we get the answer, yes. All is well. Why is the answer yes? Well, in this case, it's very easy to explain. Whenever a computation reaches a request, then it will have to reach state 5 eventually. So every request is eventually followed by a grant, so the property is true. If we modify the system slightly and add a self-loop on state 3, and we ask again, is it true that every request is eventually followed by a grant? We run this through a model checker, and the model checker tells us the answer is no. And the model checker also tells us why the answer is no. The answer is no because here is a counterexample. This is a computation of the system, 1, 2, and then stay in state 3 forever. And this counterexample violates the specification. So this is model checking in a nutshell. Now, this basic paradigm has been a great success story since around the 80s. It generated several Turing Awards, Canelakis Awards, software awards, and it's actually being used in practice, mainly by hardware companies and others. But also in the past few decades, it's getting towards code verification and software verification, which is a very interesting application. It's very difficult computationally, but it's being done. Now, I haven't mentioned yet exactly what kind of systems we look at and what kind of specifications we look at. And the reason is that if you change the specification and or systems, so this is just a list of all kinds of models, whenever you change those, the complexity of the problems we look at becomes hugely different. And this also means that the tools we need to use vary a lot in the techniques and the basic structure that underlies the problem. So we have things solvable in p-time, and we range all through the complexity scale to problems that we only know are decidable without complexity bounds, a lot of undecidable things, and of course a lot of open problems. So the point of this is to demonstrate that we have this huge, vast area of problems, techniques, and things to be looked at. Right. Now, a very interesting application of model checking is in robotic planning. What is robotic planning and what does it have to do with model checking? So in robotic planning, we're given an environment. In this case, we have this world. We have Wally here. We have a plant here, and this is Wally's home, which you can't see very well. And Wally has a goal. The goal of Wally is to find the plant and bring it home. So what we want to do is to find a plan for Wally to achieve this goal. Find some path that leads Wally to the plant and then home. What does it have to do with model checking? Well, this is actually kind of an instance of model checking in the following sense. Take a system that is constructed by the state space of the environment, or the model of the environment, compose the model of the environment with the model of the robot. So Wally's model here is some kind of state machine. Take this composition and then take the following goal, or the following specification for Wally. The specification is Wally cannot reach the plant and go home. If the specification holds in the system, then Wally cannot reach the plant and go home. So we're done. But if the specification is violated, then there is a counterexample. And this counterexample is exactly a plan for Wally to take the plant and go home. So I view robotic planning as an instance of automated verification, and I will treat it as such later. OK, so let's go back to our paradigm of model checking. One drawback of this paradigm in its current form, in this form, is the following question. Suppose you design a system, this huge state machine, and you've written your specification, this long formula, and you run them through a model checker, and it runs for hours and hours, and it halts and it says, yes, your system does satisfy your specification. It's kind of because how would you know that? How would you believe the model checker? What kind of insight did you gain by this yes answer? The answer is not much. So the question is, how can we certify or explain the yes answer of the model checker? And actually, this question also makes sense for counterexamples. So you've got a counterexample from the model checker. How would you understand this counterexample? And this requires a bit of justification on my end. So let's go back to our setting with Wally. And I think that counterexamples are too convoluted to understand, at least for humans, at least in this context. And why is that? Because this path that I drew here is not actually the counterexample. It's just kind of an abstraction or an interpretation of the counterexample. The actual counterexample talks about the robot and the environment. And it's in the language of the robot and the environment. So it will look something like this. Turn some degrees, then increase your speed, then wait, then turn again, then decrease your speed, then wait again, extend your arm, pick up the plant. This is not readable for a human. So, and even a simpler counterexample, think of yourself in a car navigation scenario. You ask for directions from point A to point B. If the answer you would get is turn your steering wheel 7 degrees, then accelerate in this pressure, and then decelerate, and so on, you wouldn't understand why this takes you from point A to point B, and you wouldn't believe it. It makes sense that you wouldn't believe it. What you want to see is the actual path on the graph that will take you from point A to point B. So we want to somehow explain these counterexamples as well as the yes answer of the model checker. And now the question is, how do we explain things? What is an explanation? What is a certificate for the correctness of something? So this is, of course, a very general philosophical question, which I will not attempt to answer. But we identify some fundamental properties of explanations that we want to reason about and consider. And these properties are soundness, completeness, and simplicity. So soundness is the following property. If a certificate exists, then the system is correct. So if I show you the certificate, you should become convinced that the system is actually correct. Completeness, dually, says that if the system is correct, then the certificate should exist. And simplicity says that the certificate should be easy to understand. What does easy to understand mean? As my PI puts it, we want to convince not only the designer, but the designer's grandparents. So this is a formal definition of simple. So let's look at these properties. The notion of soundness, something that is sound and complete, I will call proof. And the reason is that we often think of proofs as sound and complete systems. And these are not simple things to read. So this is a certificate, definitely. It definitely convinces you that something is correct. And if the thing is correct, then you have a proof. But it's not simple. So it's not really the notion we want to look at. And also, this is a very well-studied notion. So our contribution here would not be significant. How about things that are simple and complete? So these are type of certificates which I will call diagnostic information. And the reason is that they provide information that will help you become convinced, but they won't necessarily convince you. For example, if I want to explain why something is a guitar, I can show you 6 strings. And this is complete information. If it's a standard guitar, I can show you 6 strings indeed. But that won't convince you necessarily because there are other things with 6 strings that are not guitars. So this is kind of information that will help you become convinced. And the last notion is things which are simple and sound, and these I will call explanations. And I find this the most interesting notion. And the reason I call this an explanation is in the following sense. If you have some phenomenon and I can explain it to you, that means I can give you some simple piece of information that will make you understand the phenomenon. But on the other hand, there are some phenomena that I cannot explain. So this is not necessarily complete. So this is a nice diagram of the notions we study. But actually what we want to study is the quantitative manner of treating these properties. So things can be more complete, more simple, less simple. And I will show concrete examples as we go on. And it's very interesting to look at the trade-off between these properties. So supposing I can get something that's both simple, that's all simple, sound, and complete, but I can get things with certain trade-offs. What are these trade-offs? What do they mean? So this will all become much clearer as we go on. What do I want to talk about today? So I will present two works from very, very different contexts in verification. One is from robotic planning, air traffic control, and the other is about linear dynamical systems. And the idea is that we need to focus our context to some scenario where explanations make sense. So these are two things in different areas that make sense in the explanation sense, the explanation domain. So I'll start with the first work, which is about air traffic control, or in other words, disjoint path decomposition in multi-agent pathfinding. This is ongoing work with Morteza Lahianian from Colorado University. So what is multi-agent pathfinding? It's a very well-known problem, the following. We're given an environment. I'm not saying how it is given. It could be a graph. It could be continuous, some environment. And we're given a set of initial locations of k agents. So S1 to Sk are initial locations for agents. And we have target locations for these agents. And the goal in multi-agent pathfinding is to find a path for each agent to reach from its source to its target, such that if they all take their path simultaneously, they don't collide. Okay? A very natural problem in air traffic control, in drone navigation, in autonomous cars. You don't want your agents to collide. And what we want is to explain the output of the plan. So what is the plan? The plan here is the set of paths that the agents take, and we want to explain it. And a good question is, what does it mean to explain it? So we'll get to that.
So there's no aspect of time control here? Everybody moves at the same speed?
I'm not saying anything about moving at the same speed because the environment, the paths themselves could incorporate the speed in it. And this will become evident immediately. So this is an application of that. It's air traffic control. You have planes here, and each plane has its target. And this is a no-flight zone, so the planes have to somehow navigate around it. And we don't want the planes to collide. So we want to find non-colliding paths for the airplane. We run this through some multi-agent pathfinding algorithm, and we get as output the following plan. The planes fly around. I'm super proud of this animation. They fly around to get to their targets. And the question is, was this a good plan? And if it's a good plan, how can I explain it? So how do I even present this plan to an air traffic controller? One way is to present this animation that I've just showed. And I don't know if all of you managed to follow the 3 planes and make sure they didn't collide, but think of what happened if you have 20 planes or 100 planes. It's nearly impossible to view this carefully enough to see if they don't collide. You have to view it very, very, very slowly, which takes a huge amount of time, and it doesn't make sense in air traffic control where you actually have to make decisions about these trajectories. So the way we present this to the controller is as a set of paths, so just what you see here. And the question is, what do we want to explain about this setting? So there are 2 properties that should hold. The first property is that every path should lead from the source to the target. So every plane should get from where it is to its target. And we claim that this doesn't really require explanation. And the reason it doesn't require explanation is because you can view each plane separately. It's very quick. It's not really problematic. We assume that the controller can trust this property. What we do need to explain is why the agents don't collide. And again, as we said, showing an animation is not reasonable. So how can we explain this? We suggest the following notion. Take t to be the length of the plan. So t is the maximal time that it takes for a plane to reach the target. And we're going to decompose this time into segments such that within every segment of time, the paths are completely disjoint. What do I mean? So let's fade out the plan. The first segment will look like this. So up to the first time point, the green plane flew all the way here, the blue plane flew here, and the red plane flew here. And you can see that the speeds are not constant. So the green plane is much faster than the red plane. But the paths are disjoint up to here. So the planes definitely didn't collide up to time t1. Then we'll look at time t2. So from t1 to t2. So if you look at the green line, you can see that it starts from where it ended. And this is the second time frame. And here the planes also didn't collide. And this is the third time frame, fourth time frame, fifth time frame. And it's very quick to verify that the paths are disjoint. It's visually clear. So with 5 pictures, I've managed to explain why the planes didn't collide in this whole animation. And we claim this is a good paradigm for explaining non-colliding paths. So let's make this slightly more concrete. The multi-agent pathfinding on graphs is the following problem. We're given a graph with vertices and edges. The source are now vertices, the targets are vertices, and we get some time-bound t. And what we want to decide in the decision version of the problem is whether there is a set of non-colliding paths for each agent of length at most t. So this is a very well-studied problem. Yeah?
So why is it better than not sort of adding another dimension, which is time, and then it extended sort of dimensions, the paths of this theorem?
Good question, because so how would you visualize time? actually, air traffic control is 3. So the thing I showed here is just a toy example. But what if you have 3D navigation? And then you need another dimension, you can't really visualize that. But you're right, this is... in this context, we explain the plan to a human. So the type of explanation we use is visual. Yeah. Will not be the case in the second work. Right, so this is a well-studied problem. And what we add in the naive approach is an explanation of the result. So you run an algorithm for this, you get a non-colliding set of paths, and then you also get some parameter m, which you can think of as the simplicity parameter, how many segments I have. And what I wanted is to decide if there exists a disjoint decomposition with at most m segments. I want to see if I can split it to a small number of frames. So this is a fairly interesting problem, but a much more interesting problem, also in a general sense, is to plan with explanations in mind. So now I'm given the entire input for the planning instance, so the graph, the source vertices, the target vertices, the time bound, and I'm also given the simplicity parameter. And now I want to decide, can I plan such that I will have an explanation with at most m segments, and the time will be at most t. And this gives us a nice trade-off between completeness and simplicity. So if I allow a lot of segments, then I can easily plan, or it's easier to find plans because there are more of them. But the explanation will take a lot of frames. On the other hand, if I tune down the explainability to, say, 1 frame, then I might not be able to plan at all because they require disjoint paths. Or I might be able to plan, but I might need much longer time. So this is a very interesting trade-off to look at. Right, so these are the problems we study. What are the results? Well, they're a bit unfortunate. Multi-agent pathfinding is NP-complete. This is very well known. But it's not hopeless in the sense that there is a lot of work on it. And there are many good heuristics or approximations for the minimal time. So there is hope of actually doing it, and it's being done in practice because it's very, very important. On the positive side, if we're given a solution for multi-agent pathfinding, then we can find an optimal decomposition to a minimal number of segments in polynomial time. And the algorithm is very simple. It's just greedily try to go in time as much as you can until the agents collide. When they collide, stop just before that, and then continue from there. So that works very easily. And of course, the general problem of planning with explanations in mind is NP-complete. But our hope is that these techniques might give us some option of solving this. But we don't know yet. Right, so this is a very naive example, or a very preliminary example of explaining multi-agent pathfinding. Of course, there are a lot of extensions that we want to look at. The first one is continuous dynamics. So I showed the formal problem on graphs, but my example was from the continuous domain. So of course, we want to actually be able to do this in a continuous fashion. The thing is that exact planning with continuous dynamics is not really done in practice. It's not feasible almost at all. So what's usually done is to discretize the continuous scenario to a discrete setting, plan there, and then lift the plan back to the continuous setting. And in our context, we need to make sure that the discrete explanations also make sense in the continuous domain. So do they carry between them? Another extension is to look at explainable planning for reactive agents. So again, in our example, the robots just took their paths to the target, and that was it. But actually, usually, the robots interact with an environment. So the robot reaches a door. If the door is open, it does one thing. If the door is closed, it does another thing. Now we want to explain this branching program. How do we do that? That remains to be seen. And we want to look, of course, at things beyond reachability objectives. So first of all, to general Boolean objectives, such as Wally, get the plant and go home. Don't just go home. And things that take infinite time. So robots that continuously work in their environment, such as vacuum cleaners. And quantitative objectives. So not just whether you can achieve your goal, but how well can you achieve your goal. In the context of, for example, air traffic control, can I find a plan where the planes are very far from each other, or very close to each other, or things like that, or very fast, very slow, quantitative properties of the program. And we want to look at other kinds of certificates, specifically diagnostic certificates, so not things that are sound, but things that are complete, such as the distance between the agents. So I want to find a plan, and I also want a parameter that tells me how close do the planes get in the minimal, how minimally close do they get. And that's information about the plan that will help me trust the plan or pick one plan over the other. And number of non-idle operations. This is an interesting notion in air traffic control. So in air traffic control, the controller gives directives to the planes where to go. And you don't want these instructions to be given too quickly. So you don't want the plane to start zigzagging around. You want an instruction to be given every few minutes. So the number of these instructions we want to minimize. And this is kind of a diagnostic certificate about how good a plan is. If the plan is very good, then I'll have a minimal number of instructions to be given. So this is about explaining things in the robotic planning context. If you have any questions about this, it's a good time because, okay. So moving on to the second work, and this is a very different type of work. If you've lost me so far at any point, this is a good time to come back. This is about invariant synthesis for linear loops. This is joint work with Dmitry Chistikov, Joel Wachner, and James Swirl. It was presented at ICOP this year. And as you'll see, this is a bit mathematically heavy, so stop me from going too fast. And it's a very different type of context in which explanations make sense. And the explanations there are not explaining to a human, but rather explaining to a computer that can verify the certificate. But more on that as we go on. So what are linear dynamical systems? What are linear loops? A linear loop is a very simple program of this form. We have some initial vector s, and we assign this to a variable x. And then we have a loop, which updates x over and over and over by applying some update matrix A. So we just apply A over and over and over and over to the vector s and see where we get. And if we reach a terminating set f, then the loop halts. Very simple program. And these arise in practice when we do verification on code that has some linear behavior. We often abstracted the entire code to the linear behavior and reason about that in the hope that a counterexample or a bug here will induce a bug in the original system, because general code is too difficult. So we associate with this thing a linear dynamical system, which is the same thing as the linear loop, only we ignore the terminating condition. So we just have a matrix and a vector, and we apply the matrix over and over and over to the vector and see where we get. And this set of points that we see is called the orbit. Okay, so this is the model we study. Let's see an example of that. So for the example, we'll be in 3D. We have the point 1, 1, 1 here. This is S. And we have some update matrix A. What does this matrix do? On the z-axis, it multiplies by 5. So every step, we multiply by 5 on the z-axis, and we climb up. On the xy plane, what this is simply twice the rotation matrix by theta. So we rotate by theta. We stretch by 2 on the xy plane, and we climb by 5 on the z-axis. So what's going to happen when we apply this matrix over and over? We're going to start rotating and climbing, and we're spiraling outwards and upwards. And this is called the orbit of this system. Okay, so this infinite set of points. And if this were a linear loop, we'd also have a terminating set, and then this set can be quite elaborate and can get quite close to the orbit. So the question now is, will the loop halt? Will the loop hit the terminating set? So this is the fundamental question about linear loops. Given a vector s and a target f and matrix A, does the loop terminate? Does there exist an n such that a to the ns is an f? Okay, a very simple question. This question, as it turns out, has been open for many, many decades, even when the target is a hyperplane. So for very simple targets, we don't know how to answer this question. And this is an annoyingly open question in the following sense. Terry Tao said about it that it is faintly outrageous that this problem is still open. It is saying that we do not know how to decide the halting problem even for linear automata. And Richard Lipton called this a mathematical embarrassment. So it's open, it's been looked at, we don't know how to handle it, and things are unfortunate. You might have seen this slide before in other people's slides. Copy. What do we know about termination of linear loops? So the original problem was raised in the 70s by Harrison, and there the problem was with a singleton terminating set. So we're given two vectors, s and y, and we simply asked in the matrix A, and we asked, will the orbit of s ever hit exactly y? And this was open for roughly 10 years, until it was shown to be decidable in p-time by Cannon and Lipton, and this is now dubbed the Cannon-Lipton orbit problem. And these are two beautiful works that show that this is decidable in p-time using a non-trivial set of tools. And even in this work, Cannon and Lipton observed that when you change the target from a singleton to some relatively nice set, such as a half space, so now we have a half space f, the problem becomes considerably harder, and their tools didn't work. And there wasn't a lot of progress on this. There was some works on it. In 2012-13, Vensi Chonev, Joel Wachner, and James Swirl showed that this problem in general is hard. And it's hard not in the computational sense, so we don't know if it's decidable or not. It's hard in the sense that it has relations to long-standing open problems in number theory. So if you show that this is decidable, it will have huge implications in number theory. And actually, even if you show that this is undecidable, it will have these implications. And these problems relate to Diophantine approximation. So this is a very interesting and deep connection. They did show that it's solvable when the dimension is small enough, at most 3. And in fact, they extended this to targets that are polytopes. So slightly more elaborate targets, not just half spaces, polytopes. This is still decidable when d is at most 3, and of course it's still hard in general. A bit more recently, we looked at a dual problem, or another problem, where we quantify the set of inputs. So now instead of having a single input, and we ask, does the orbit hit a certain set, we have a set of inputs, and we ask, does there exist some input that will cause termination? And this corresponds to safety. So if you think of termination as a bad event, as an error, then what we ask is there an input that will cause an error? And if there isn't, then the system is safe. So we look at this problem when the input and out in the target are polytopes, and we show that, of course, this is still hard in general. This is solved when the dimension is at most 3. And very recently, in stacks this year, we show that this still holds when the source and targets are semi-algebraic sets. If you don't know what that is, I'll explain it in a minute. But this is basically as far as you can get in dimension 3, because things beyond semi-algebraic are often not known to be decidable. So this is like the kind of the largest decidable theory we have. So this is the state of affairs, and what you should take from this is that the problem is hard in general. Just the reachability problem of hitting a target, some target that could be very simple. So let's go back to the termination problem. Consider that you have a setting where you have an initial vector, a target, and a matrix, and suppose you know that the loop does terminate. How can you convince someone else? How can you certify that this loop terminates? Very easily. Just give the number of iterations you need to apply. So if you tell me, apply this matrix 1,000 times and it'll halt, then I'll apply it 1,000 times and check that it halts. So that's very easy to convince someone. And what we ask is there a way to convince someone of non-termination? So obviously, in general, no, because if there were a way to convince a non-termination, that the whole problem would be decidable, and we don't know that it's decidable. But maybe there is still something we can do. Maybe in some cases there exists a certificate for non-termination, and we can provide that. So this is what we focus on in this work. So what would be such a non-termination certificate? Very naively, it'll be a set I that contains the orbit and doesn't contain the target. So it separates the orbit from the target. If there is such a set, then the loop doesn't terminate, obviously. Thing is, this still doesn't mean that I have a certificate, because maybe I is very complicated to explain to someone. So I want I to be simple. And if I is simple enough, then, for example, if I is a half space, then I can't even check that. So I can give someone the explanation, but they can't check it. So I didn't actually do anything, because the problem of checking whether the orbit is contained in it is equivalent to the termination problem. So the question is, how do I overcome that? And obviously, now we need to actually assume something, because otherwise I'll have a complete explanation. So what we do is split this requirement into two requirements. The first one says that the initial vector is an I, and the second requirement says that I itself is invariant under the matrix. So if you take a point in I, apply the matrix, you'll stay within I. And these two requirements together imply that the orbit is contained, because the initial point is there, and whenever you apply the matrix, you stay within the set, so the entire orbit is there. And these two properties are much easier to verify than reasoning about the orbit. So almost formally, the problem we look at is finding sets with these properties. The thing is, I haven't said what simple to describe means yet. And this is not formal, of course, so we need to formalize it somehow. And for that, we'll take a small detour to explain what kind of sets we allow as simple. So the way we formalize simple sets are using are sets that are definable in some O-minimal theory. What are O-minimal theories of the reals? Formally, a theory is O-minimal if every set that you can define on the real line consists of a finite union of points and intervals. The intervals could be unbounded. If you don't completely follow that, don't worry. Whenever I say O-minimal, you can just think nice sets. What's nice about them? First of all, O-minimal sets are closed under lots and lots of operations. I will mention which operations when I need them. And secondly, an O-minimal set consists of a finite union of connected components. Specifically, the orbit is very much not O-minimal. The orbit has infinitely many discrete points usually. So the orbits are not O-minimal. Nice sets are, O-minimal sets are nice. What kind of O-minimal theories have you seen before, and you probably know a bit? So the first one is R0, the first order theory of the reals, also known as semi-algebraic sets. These are sets that are definable using polynomial equalities and inequalities with integer coefficients. For example, in R2, the set of points x, y, such that this polynomial inequality holds, and this polynomial inequality holds, defines this right half of the disk. So this is a semi-algebraic set with one connected component. You could have here or something else, which will add another connected component. And these are simple sets, or minimal sets. And the first order theory of the reals is known to be decidable. Another example which you might have seen is Rx, the first order theory of the reals with exponentiation. So the same thing, I allow polynomial equalities and inequalities, and also the exponential function. For example, the set of points x, y, such that this exponential equality holds, y equals e to the x, and x squared is at most 1, polynomial inequality. This defines the graph of the function e to the x between -1 and 1. So this orange line here is a set definable in Rx. And it has, again, one connected component. And this theory is not known to be decidable. It's almost known to be decidable. I'll mention that later. So we'll mostly focus on these theories, but in general, we allow O-minimal sets. And this is what simple to describe means as far as I'm concerned. If you didn't completely follow that, when I say O-minimal, think nice. Right, so now we have the following problem. We're given a vector S, an O-minimal target F, and a matrix A, and we want to decide whether there exists an explanation. So does there exist an O-minimal set that contains the initial point, is invariant under the matrix, and is disjoint from the target? So does there exist an invariant explanation for non-termination? And this, the invariance is where we restrict the class of things we look at. So we want not only sets that contain the orbit and are separate from the target, but nice sets and invariant sets. And we look at a variant of this problem for linear dynamical systems where we don't have a target. And there we just ask for a set I, an O-minimal set I, that contains the initial point and is invariant under the matrix. Now, of course, this problem doesn't really make sense because you can take the entire space, which obviously satisfies these. So we want some kind of a minimal set, or a smallest set. And this will become clearer when I define these sets. And note that we also here look at O-minimal targets. And the reason is that if your target is not O-minimal or not even semi-algebraic, then you can't even check membership. So there is no real point in even providing a certificate because the target is too elaborate. So these are the problems we look at. What can we say about these problems? So I will try to explain now how we characterize these invariants and what kind of properties they must satisfy, and then I'll prove that later. So we look at a linear dynamical systems AS, and we want to find an O-minimal set I that is invariant under the matrix A. It contains the S, and it contains the entire orbit. So it contains the initial point and is invariant under the matrix. And again, we'll look at the example we had before with this matrix and this vector. Now, this matrix is a bit hard to analyze. What I would do is diagonalize it. So every matrix can be either diagonalized or put into Jordan form. This matrix can be diagonalized. And I'm going to lie a bit. Oh, sorry. This is the orbit that we've seen before of this linear dynamical system. And I'm going to lie a bit and write this matrix as a diagonal matrix, ignoring the similarity matrices. So I'm just going to assume that A equals this matrix. What is this matrix? So on the Z axis, it has on the diagonal, it has the eigenvalues. On the Z axis, it has this eigenvalue 5, which is real. On the X and Y plane, it has two complex conjugate eigenvalues. What are these eigenvalues? So lambda is a complex number on the unit circle, so a complex number of length 1. And the modulus of the eigenvalue 2 lambda is 2. So we stretch by 2 and rotate. So this is what this signifies. And when we take the nth power of A, we simply get the nth power of the diagonal, which is why we use the diagonal form. It's easier to reason about powers. And then we multiply this by S, and we get the following vector: 2 to the n lambda to the n, 2 to the n lambda conjugate to the n, and 5 to the n. So all points in the orbit are of this form, which means that the orbit is simply the set of these points. So all the points here are of this form. And now we want to think about how would this invariant look like. So what kind of properties it has to satisfy. And the first thing we're going to do is look at some kind of normalized orbit, which is equivalent to the following idea. Let's look at the first point here. So when n is 0. When n is 0, this becomes 1, this becomes 1, and this becomes 1. And I'm going to leave lambda to the n and lambda bar to the n as lambda bar to the n, and look at where they rotate. And the intuition is that if I is invariant under the matrix, then if it contains some point, then it has to kind of contain all the points where you rotate lambda around it without climbing modulus. This is not true. We'll go with it for now. So what kind of set do we get by looking at this normalized orbit? We take the first point on the orbit and rotate it without changing the modulus, and we just get this unit circle. What is this unit circle? Well, it's the set of points of modulus 1. Set point z, z bar 1, where z is a complex number of modulus 1. So this is just a circle, basically. And the intuition that if I is also nice, then not only will it contain every point that rotates around the first point, it will also contain the entire closure of that, so the entire circle, because it's nice. And nice sets should be like smooth. Now, there wasn't anything special about taking n equals 0 here and taking 1, 1, 1. We can do this for every point on the orbit. So what we would get is the set of rings for every point, we have a ring that should be in the invariant. This is just intuitive for now. But this means that the orbit should be contained in the set 2 to the n, 2 to the n, 5 to the n, but I replace lambda to the n and lambda bar to the n with z and z bar from here. So the orbit is contained in this union of rings. Now, I is an O-minimal set, so it cannot contain these rings separately, because it has only finitely many connected components. So it has to contain some kind of smooth version of these rings, namely this bowl-shaped thing. So what is this bowl-shaped thing? We need to somehow smooth out this discrete n. And the way we do it is very simple. We write n equals log t for some real number t. And then 2 to the n becomes t to the log 2. 5 to the n becomes t to the log 5. And we can write that the orbit is in the set t to the log 2, t to the log 2, t to the log 5 times z, z bar 1, where z is a complex number of modulus 1, and t is just a real number. And this set defines this bowl-shaped thing, which we call trajectory cone. And what we prove is that take any O-minimal invariant I, then it must contain this entire cone, almost, from some height. So you can chop the bottom part of the cone, but from some height, the invariant has to contain the entire cone. And this is the idea. And I'm going to give a brief sketch of this proof. And for that, I need to somehow formally define these cones, not only in 3 dimensions, but in higher dimensions. So in general, we can do the same treatment we just did for 3 dimensions in diagonalizable matrices. And we get that the orbit is contained in this kind of set, so t to the log things, just as we had before, where instead of a complex number of modulus 1, we have this set t, which is not important. I'm not going to go into that, but think of this as a circle. And the trajectory cone is then defined with respect to some number t0, which is where we chop it from. So ct0 is the cone chopped from t0. And we're also going to define something called a trajectory ray. This is for the proof's sake, which is what happens if you fix a point on the circle and just smooth the moduli without rotating. So this is on the surface of this cone, you get this ray thing. Okay, and this is for the diagonalizable case. We can also do this for the non-diagonalizable case, and then things become slightly more complicated. So we also have this polylog factors here. And the reason I drag you through all these awful technical details is to say the following. The trajectory cone and the trajectory ray are definable in Rexp. So they're all minimal sets, and they're kind of nice. They're definable in a reasonable theory. And the reason we need Rx is because we need these logs here. And for that reason, they're not definable in R0, which is kind of unfortunate. It means that it's not necessarily decidable whether a point is in them or not. So they're nice set. They're not super nice. And this is the important thing. Right. So what do we show about these sets? 2 things. We show that, first of all, they are invariants. So they're kind of sufficient for invariance, in the sense that if you take the cone and you add to it the finitely many points that you've left beneath it, then you get an invariant for the linear dynamical system. And this is not very difficult to prove. The interesting thing is that if you take any O-minimal invariant for the linear dynamical system, then it must contain the cone from some height. So in a sense, cones are sufficient and necessary conditions for the existence of an invariant, an explanation. So I'm going to give a brief sketch of the proof of this. So we want to prove that if I is an O-minimal invariant, then it contains the cone from some height. How do we prove that? We start by looking at the rays, and we first prove that every ray is eventually in the invariant or eventually out of the invariant. A ray cannot go in and out, in and out, in and out of an invariant. Why is that? Well, take the intersection of the ray and the invariant. So you get some parts of the ray that way. And the ray is O-minimal. The invariant is O-minimal. Their intersection is therefore also O-minimal, because O-minimal sets are closed under intersection. So this is an O-minimal set. But an O-minimal set has finitely many connected components. So either this thing has an unbounded component, in which case the ray is eventually inside the invariant, or it doesn't, in which case the ray is eventually out of the invariant. So that was very simple. Now we're actually going to strengthen this claim and say that every ray is eventually in. No ray can be eventually out. Why is that? So suppose some ray was out. And suppose some ray was entirely out for the sake of the drawing. Let's look at the inverse image of this ray under the matrix. This thing is also a ray. This is just because of the definition of rays. But this ray also has to be out, because if this ray were in at some point, then the image will also be in because the set is invariant. So I have another ray that's out, and I can continue in this fashion, taking inverse images. And what I'm going to get eventually is a dense set of rays that are out. So what do we have? We have an O-minimal invariant, a nice set, that contains the orbit, but doesn't contain a dense set of the cone. Nice sets cannot not contain a dense set. If you take out a dense set from a nice set, you get nothing. You can't leave just discrete. It's a lot of infinitely many points. So what we get from that is that the invariant will not contain any of the cone. In particular, it won't contain the linear dynamical system, and that's a contradiction. So what we get is that every ray is indeed eventually inside. And this almost proves what we want. It almost proves that the entire cone is there from some height. The thing is that it might be the case that these rays are eventually in, but the eventuality is unboundedly growing. And we actually show this is not the case, but I'm not going to show it now. So we proved our claim. And we proved that there exists an O-minimal invariant I for the linear dynamical system that avoids the target f, if and only if I can use the cone as an invariant. So if and only if the cone avoids f, and the points that you left behind also avoid f. So this is the characterization of the existence of invariants. But the question is, can we decide if there exists an invariant? Can we decide if there exists such a T0 such that this holds? So deciding the existence of an invariant amounts to deciding the truth value of this sentence. Does there exist T0 such that the cone doesn't intersect the target? The cone from T0 doesn't intersect the target. And the question is this simple sentence decidable? Well, if the target itself is Rx definable, then this entire sentence is definable in Rx, because this set is also definable in Rx. And Rx is, as I said, not known to be decidable. It is known to be decidable subject to some conjecture in transcendental number theory called Chanuel's conjecture. And the dependence on this is nice in the sense that if Chanuel's conjecture is true, then we have an algorithm for deciding this. If Chanuel's conjecture is false, then we have an algorithm that will never give the wrong answer but might not halt. So bad, but not too bad. The surprising thing is that if f is R0 definable, if it's semi-algebraic, then this whole sentence is decidable. And this is surprising because CT0 is not definable in R0. And this is unconditionally decidable. And to prove that, we need to use some deep results from number theory, such as Baker's theorem. Baker's theorem. Now, moreover, when we can decide that there exists an invariant, we can also find one. We can synthesize an invariant, which is the cone. And more surprisingly, if f is semi-algebraic, then we can synthesize a different invariant, which is kind of a fat variant of the cone, which is also semi-algebraic. So this is quite surprising. This is not published yet, but it's under submission almost. Right, so to sum up this work, deciding whether a linear pulse is a long-standing open problem, and we provide invariants as certificates or explanations for non-termination. And invariants, in fact, prove non-termination not only for the point you started with, but for every point on the invariant. So it's quite a big set of points. And we provide algorithms for invariant synthesis for a very broad class of terminating sets, all O-minimal sets, which is a huge class. And our invariants are minimal in a sense. And moreover, we provide unconditional decidability when the target is semi-algebraic. So this is proper decidability, not conjectured. Now, for future work, we want to look at two directions. One is what happens when you have more than one update matrix. So I can either apply A or apply B at every point. And this represents non-determinism in the system. And these elicits much more complicated behaviors, and it's not clear what can be said about this. It's a much harder problem. Something that's more reasonable is looking at invariants for systems with control. So now at every point we apply a matrix, and we also have some user input. And we want to see where that gets, and we want to synthesize invariants for that. So this is work in progress. So what we've seen are two very different contexts where explanations make sense. One for humans, one for machines. But these are things we can explain. And the techniques used to explain them, which are very, very different. And in general, certifying the results of automated verifications enables us to trust the system, to understand it, to gain some insight on the workings. And this is something very desirable. Unfortunately, there is no right definition of explanation in the most general sense. So what we need to do is focus on specific contexts. And the way to do that, one is to look at practical applications, such as air traffic control. And the restriction of the domain there gives rise to some reasonable definitions of what can be explained and how it can be explained. Alternatively, we can look at domains that have a lot of algebraic structure under them, such as dynamical systems, where the rich language that we have allows us to describe things that we cannot describe in general, such as invariants. And it's very interesting to look at the trade-off between the soundness, the completeness, and the simplicity of the various types of certificates we get, and what does it mean on the certificates, and so on. That's it. Thank you.
Just to be sure, I mean, you did it for an arbitrary matrix that you can diagonalize or arbitrary matrix?
Arbitrary matrix.
So what happens if you have, when you diagonalize, you have entries above the...
So this is where you get this polylog things that I showed briefly. This is the reason, basically, if the matrix is diagonalized, then the things you would get are not semi-algebraic, but they're really almost semi-algebraic in the sense that you just need constant powers that are not rational. But it still might be decidable. But if it's properly non-diagonalizable, then it's really Rx definable.
About the adding LTL, how difficult will it be?
So adding LTL to dynamical systems, we looked at that. It's reasonable only in 3 dimensions at most, because up from that we don't know anything. It seems that it perhaps can be done. There are some simpler problems that we still don't know how to do. It seems like it would require a lot of different cases that are all fairly simple. So we tried to look at it a bit, and the number of cases exploded. So if you have a fleet of master students, this seems like a reasonable task to approach. But it just requires a lot of manpower to do. It doesn't seem to generalize well, in a way. That seems to be doable.
Thank you very much.
Thanks so much.